Today we are going to learn about an algorithm handling dynamic environments. We'll explore how to adapt A for dynamic settings, focusing on real-time changes essential for applications like autonomous vehicles. You'll gain skills in modifying A to handle environments that evolve over time. Welcome to our deep dive into the A algorithm and its application in dynamic environments. The A algorithm is a popular pathfinding and graph traversal algorithm used extensively in computer science. It finds the shortest path between nodes, a crucial function in fields like robotics, simulations, and game development. However, applying A in dynamic environments, where conditions change in real time, poses significant challenges. This video will explore these challenges and introduce strategies to overcome them. We'll cover dynamic pathfinding strategies, incremental search techniques, and real-time replanning. By the end of this video, you'll understand how to modify A for environments that change over time, enhancing its performance in real-world applications like autonomous navigation systems. In dynamic environments, the main challenge for the A algorithm lies in its rigidity. Standard A operates under the assumption that the environment is static, meaning it doesn't account for changes that might occur after the initial path has been planned. This becomes problematic in real-world scenarios where environments are rarely static. For example, an autonomous vehicle navigating a busy street needs to adapt to moving obstacles, changing traffic signals, and unexpected road conditions. The limitations of standard A in such settings can lead to inefficiencies, as the algorithm may require complete recomputation of paths whenever changes occur. This is not only time-consuming but also computationally expensive, highlighting the need for more adaptive strategies. Real-time processing is crucial, as decisions must be made swiftly to maintain optimal pathfinding and avoid potential hazards. Understanding these challenges is the first step toward enhancing A for dynamic environments. Dynamic pathfinding represents a shift from static algorithms, requiring the ability to update paths on the fly as conditions change. Unlike static pathfinding, dynamic strategies are designed to handle unpredictability, allowing for the reassessment of paths in real time. This adaptability is achieved through a variety of methods, including incremental search, where only the affected portions of the path are recalculated, and the use of heuristics that can adjust based on real-time data. Dynamic pathfinding strategies often borrow from existing algorithms, modifying them to incorporate adaptability and efficiency in changing environments. For instance, algorithms like D-Light and Anytime Repairing A have been developed to enhance A by focusing on minimizing recalculations and improving time efficiency. Real-world examples include robotics and game AI, where dynamic pathfinding ensures entities can navigate effectively amidst changing obstacles, leading to more realistic and responsive systems. Incremental search techniques play a pivotal role in adapting the A algorithm for dynamic environments. The core idea behind incremental search is to update the path incrementally, rather than recalculating it entirely from scratch whenever a change occurs. This approach significantly reduces the computational cost and improves efficiency, making it highly suitable for real-time applications. Incremental variations, such as D-Light and lifelong planning A, enable the algorithm to efficiently manage changes by focusing on recalculating only the affected parts of the path. This selective updating process ensures that the algorithm can adapt swiftly to new conditions, maintaining optimal performance. The benefits of incremental search are particularly evident in scenarios involving frequent changes, such as navigation in crowded areas or dynamic gaming environments, where speed and accuracy are paramount. Real-time replanning is a crucial component of dynamic pathfinding, especially in applications where time is of the essence. In environments that are constantly evolving, the ability to replan efficiently and effectively is vital to ensure that decisions are based on the most current information. Real-time replanning addresses the challenges posed by dynamic conditions by allowing algorithms to reassess and adjust paths as new data becomes available. Techniques such as prioritized sweeping and focus D enable more efficient replanning by targeting the most critical areas for recalculation. The impact on decision-making is profound, as timely adjustments can mean the difference between success and failure in high-stakes scenarios. For example, in autonomous navigation systems, real-time replanning ensures vehicles can react promptly to sudden changes in traffic or obstacles, maintaining safety and efficiency in their operations. Autonomous navigation systems serve as a prime example of applying the A algorithm in dynamic environments. These systems must navigate complex, constantly changing real-world settings, requiring robust and adaptable pathfinding solutions. A is often integrated with sensor data to assess the environment and make informed decisions. Challenges include dealing with moving obstacles, varying terrain, and unpredictable external factors. Solutions involve integrating A with real-time data processing and sensor fusion to continuously update and optimize paths. Autonomous vehicles, for example, rely on A to plot efficient routes while reacting to live traffic conditions, ensuring safety and performance. The future of autonomous navigation will likely see further enhancements in dynamic pathfinding, with adaptations playing a central role in achieving fully autonomous systems capable of handling any environment. In this section, we'll walk through the process of coding A for dynamic environments, focusing on handling real-time updates. We'll start by setting up a basic A implementation, then introduce modifications to accommodate dynamic changes. The key is to incorporate incremental search techniques, allowing our algorithm to update paths efficiently without complete recalculation. We'll demonstrate this with a practical coding example, highlighting how to handle dynamic obstacles and changing goal conditions. Developers should consider factors like computational resources, update frequency, and the complexity of dynamic elements when implementing these systems. This demonstration will provide a hands-on understanding of how to adapt A for dynamic worlds, equipping you with the skills to tackle complex pathfinding challenges in real-time applications. Evaluating the performance of A in dynamic environments requires a different set of metrics compared to static scenarios. Key metrics include response time, path optimality, and computational efficiency. The challenge lies in balancing speed and accuracy. The algorithm must adapt quickly to changes without compromising the quality of the path. Tools such as simulation environments and real-time analytics can aid in testing and analyzing performance. These tools allow developers to measure the impact of dynamic changes on pathfinding efficiency and identify areas for improvement. Enhancing system robustness involves optimizing the algorithm to handle a wide range of conditions, ensuring reliability and performance consistency. By focusing on these aspects, developers can create dynamic pathfinding systems that excel in ever-changing environments. Integrating machine learning with the A algorithm opens new possibilities for dynamic pathfinding. Machine learning techniques can enhance A by providing predictive analysis and adaptive heuristics, allowing the algorithm to anticipate changes and adjust accordingly. This integration is particularly beneficial in complex systems where traditional pathfinding methods struggle to keep up with the dynamic nature of the environment. Applications range from autonomous vehicles, where machine learning can predict traffic patterns, to advanced simulation games that require intelligent NPC navigation. By leveraging AI, I can become more resilient and efficient, capable of handling even the most unpredictable scenarios. The future of pathfinding will likely see further convergence of these technologies, with machine learning playing an integral role in developing smarter and more adaptive algorithms. In conclusion, adapting the A algorithm for dynamic environments is not only beneficial but essential for modern applications. We've explored the challenges of implementing A in real-time settings, introduced dynamic pathfinding strategies, and demonstrated coding techniques to handle changing conditions. As we look to the future, the integration of advanced technologies like machine learning will further enhance AI's capabilities. We encourage you to continue exploring this fascinating topic and apply these insights to your projects. Thank you for joining us in this exploration of A in dynamic environments. We hope you found the content informative and inspiring.